That's right. So this, in 1.1, I was thinking about this number. I just looked at this number 6 just to kind of run through some of the ideas we did yesterday. I mean, I don't always review yesterday's idea, but it's a good day for the second day of class. This is a DE, and D R squared. Well, anyway, it's a bunch of letters on the board. This is alphabet class. Anyway, there's a couple numbers up there. Hey, what do you think, let's see, who do you think is the independent variable? The independent variable, which is usually X, and it's usually the, anyway, who do you think it is in this problem?
R?
No. The independent one is usually the X, and usually we're taking the derivative of something with respect to X. This one, it looks like we're taking the derivative of R with respect to T, and this is the second derivative of R with respect to T. So anyway, I would say T is the independent variable. Those words are new to us, I know, but T would be the independent variable, and who's the dependent variable? R, yeah. And then what's that K doing? Well, K is a constant. And by the way, if you ever, in mathematics, if you see the letters A, B, C, letters toward the beginning of the alphabet tend to be constants. Letters toward the end of the alphabet tend to be variables. Kind of a unwritten rule, maybe, of mathematics. But so that K is some constant. Anyway. What's the question here? Okay, well, I asked you those questions. Let me ask you this question. What is the order of this DE?
Second.
It's second order. That's a second derivative. You know, there's, yeah. And that's one kind of complicated notation for a second derivative. You know, the other notation would be good old R double prime would work, I guess. But when you write R double prime, you don't really specify what the independent variable is, do you? When it's the second derivative of R, you kind of don't know whether you're working with X's or T's. So when you write it like that, you can see that the dependent variable R, we're taking the derivative of with respect to the independent variable T. R is a function of T, K is some constant. Okay, so you're right, it's second order because of that second derivative. And it's second order, and so then we had a good discussion on what does it mean to be a linear differential equation or not, and it had to fit this certain form, and we argued and talked about it quite a bit. What do you think about this one? Linear or not?
No.
Not, huh? Is that what you just said? Why not?
Because you're talking about X and Y equivalents. It's easier for me to translate that, but basically that's a Y on the right side.
Okay.
Which it shouldn't be.
That R is acting like my Y.
Yeah, and you'd have to multiply to get it on the left side, which would mean that you would have a coefficient that is a function of Y.
Is this an R squared or R double prime? Because we're using the numerical notation. The R, is that squared or is that double prime?
Well, now what do you think?
I would say double prime.
Wonder why. That's R double prime.
Okay. So that's R
So
squared.
this is the second derivative of R. So right. So the notation is right. The first derivative of R with respect to T is dr dt. When you do a second derivative, it's kind of funny, but it's the second derivative of R with respect to T again. That's the second derivative notation, or R double prime.
Okay, never mind.
Yeah.
R squared.
Yeah. So that's clearly an R squared. But. And just the fact that, okay, so you said a few good things actually, but I was thinking just the fact that it's an R squared, I learned yesterday that means it's not linear. That it needs to be just an R to the first. And to tell you the truth, it's not an R squared. It's down in the denominator. What it really is it's an R to the negative 2. It's an R to the negative 2 is what it really kind of is, if you moved it up. But if you moved it to the other side, it would be an R squared, and he said if you multiplied it up here, then it'd be a coefficient of this. And if you remember, we'd have to have coefficients of the coefficients had to be functions of the independent variable multiplied by the derivatives of the dependent variable. So you're right, nonlinear for various reasons, to tell you the truth, in a way. So that's all we're supposed to do. You're not supposed to solve it. This is section 1.1. You're just talking about it a little bit. You know, while we're talking about, we did just stumble onto notation just a second. Let me say this. We don't see this too often, but I just saw it in your book. I don't even know if I assigned this one, though, but I saw this notation. An X with a dot on top of it. And then a plus another X with a dot on it.
Double prime prime?
That is what that means. These dots are just another notation. You probably never saw that before, I would suggest. You've never seen that before, but maybe you have. Right, that's a second derivative, that's a first derivative of x. With respect to t, what the dots mean? The dots mean that it's definitely a time derivative. You're doing this with respect to time, with respect to t. So it's sort of a special notation that means we're definitely dealing with time. I guess every time we deal with time, we don't do that notation. Not every time, but you can use that dot notation for derivatives.
What was that problem you're looking at? When you got that from, would that be linear?
Well, that's a good question. So I'm looking at number 8 is where I see that in the book. Would it be linear? So it's not really the way I wrote it. It's x double prime minus 1 minus x prime squared over 3. See, 1 minus x prime squared over 3. See, what are you thinking?
I'm saying no.
I'm already saying no when I see this x prime, this derivative, x dot, and this derivative squared. Right, I can't have any of my derivatives or my function squared. I guess, right, so not this again, this one's nonlinear. This is number 8, nonlinear. Because of that, also maybe because it's actually now it's multiplied by another x dot. So again, the coefficient in front of this x dot is supposed to be just t's. It's supposed to be function of the independent variable t's, and it's not. So it's nonlinear again, sort of for a couple reasons. This coefficient's bad, and that thing is squared. What was I going to say? I wanted to say something else about notation. Listen, all right, so if you have a function y, and you take its derivative, it's y prime. If you take its second derivative, it's y double prime. Let's see, when you start getting to, let's see, we won't deal with this a whole lot until later, but if you get to a third derivative, y triple prime, I guess another notation for that is the third derivative of y with respect to x, or whoever the variable is. Watch this. And usually maybe it's when you get to a fourth derivative where you start to do this, but you could do it at any point, I guess. Once I go to a fourth derivative, I guess I'm sort of using Roman numerals here. So I guess I would use Roman numerals here for a fourth derivative. Or, check this out. You can put a little 4 up there, but that's confusing as hell. Now, is this a fourth power or is it a fourth derivative? Okay, well, it's a fourth power. It's not a derivative unless you do this, and you may never seen this too often, but an exponent, or what looks like an exponent in parentheses, is not really an exponent. If it's in parentheses, it's a fourth derivative of y. So that's another notation for derivatives. Fourth derivative of y. Oops. So anyway, we just fell into some derivative notation problems. You know, I hate to take all your fun away. I assigned this problem 17, and I like it. I don't really like 16 or 15. So I don't want. Sometimes I like to do problems next to the ones I assign. But I think I just want to try this 17 a second. So I'm in 1.1. I'm looking at 17. And let's see what it is. It's a y prime equals 2xy squared. So it's a differential equation. Let me ask you a question. They're not really asking this question now, but let me ask you, what's the order of this differential equation?
First.
It's a first order. And is it linear or nonlinear?
No.
It's nonlinear. Why?
Function squared.
I would see that y squared. Thank you. That's real quick. Well, that y being squared makes it nonlinear. Right. Okay. Anyway, so what? It's a DE. It's probably solvable. You know, I taught y'all how to separate and integrate, even though we're not supposed to know how to do that yet. I think you could separate and integrate this one pretty easily. But pretend we don't know how to do that. What do they give me? They give me this is the answer. Y equals 1 over 4 minus x squared. They say this is the answer. They say this is the solution. This is a differential equation, and this is the solution. And what does their question say? It's a complicated directions here. The question says, verify that the indicated function, and they call it y equals phi of x. I don't know, instead of f of x, they call it phi of x. But that's their function. They want us to verify that it's a solution of the given first order differential equation. So I taught you how to verify. How would you verify this?
Get y prime.
Yeah, just get y prime, plug it in, and it should work, I guess. Let's try it. How do I get y prime here on this problem? Y prime. Let's see.
Sign?
Well, nope. I'm taking a derivative. You're thinking of an integral, I think.
Oh, yeah.
Yeah, I'm taking a derivative. And even then, you're not quite right, actually. But I'm taking a derivative, and it's, let's see, I would move it up, right? I would call this 4 minus x squared to the negative 1. When I do a derivative, it's negative 1, 4 minus x squared to the negative 2, times the derivative inside, negative 2x. Here it is. My derivative is, let's see, if I drop him into the denominator, it's 4 minus x squared squared. The numerator becomes a positive 2x. You guys with me here? That's my derivative. It's just a nice little chain rule problem, actually, and then I cleaned it up. And so let me see. I'm supposed to verify this. So if I plug this derivative in there, I'm plugging this, I'm sort of just substituting it into this equation on that left-hand side. And then on the right-hand side, I have 2x times the function y squared. Now, there's the function y. So that original function y right there, squared. Now, is this true? Well, maybe I got to do a little work, but I don't have to do much work. If you square that function, you do square the denominator, you square the numerator. The numerator is just a 1. You move the 2x, multiply the 2x into, yeah, it's verified to me. Do you guys agree? Yep. I mean, I could write one more step maybe there, but yeah, I see it. Very clear. So cool, I verified it. Check out this next little part. I didn't really discuss this yesterday. Listen to this. Then it says, proceed as in example 2 by considering phi simply as a function. They want me to give its domain. All right. So let's do that. So if I talk about this guy as a function, I'm going to just move over here. One thing I know about this video is I try to stay between. I can't go to that board, and I can't go to that board. So I'm staying here. If I think of this as a function, what about his domain, you guys? Let's put a little thought into that. Yeah, I mean, the domain is what are you allowed to plug in for x, and so it's kind of easier to think what can you not plug in for x, and which would be kind of, I call them the bad guys. Who are the bad guys that would make this undefined? I can sort of see it. He said it's when your denominator is 0. You can set your denominator equal to 0, but I see the answers. The bad guys are 2 and negative 2. So my domain is all real numbers, but x cannot equal 2 and x cannot equal negative 2. Right. you know, on a number line, I guess, what am I saying? Like on an X number line, I'm saying my domain is all real numbers except X cannot be -2 and X cannot be 2. So it's kind of like I got a couple little holes right there. My domain is the whole number line without those 2 points. You know, it's a visual look at what we're saying. Okay, so that's the domain. Now check this out. That's the domain of this function, this answer. But when you're solving a DE, now watch, then they say, consider phi a solution to a differential equation, and now they want me to give them an interval of definition. So I skipped over this yesterday, and I don't want to make a huge deal out of it, but the book kind of does make a huge deal out of it. They kind of say that anytime you got a differential equation and a solution, you are doing this on an interval. So you're working on an interval. And you want it to be kind of a nice continuous interval without these holes in it. So the domain of this function is this picture. But an interval of definition for this answer would be one of these intervals. Either -infinity to -2. You see that? -infinity to -2. Or -2 to 2. Or 2 to infinity. And you don't really list all 3. If they want an interval. This is the solution to the differential equation and give me an interval, please. Well, you don't really list all 3. You kind of have your choice. It's one of those 3. You kind of have your choice. Usually in math classes, variables have actual meaning to real world problems, and usually you're kind of working on the right side of 0. Usually you're kind of working in quadrant 1. And so if I really was going to just pick one, I would kind of say 2 to infinity. I would say those positive values is what I'm interested in. And that would be my interval of definition. But the truth is, you're not wrong picking the other 2. It's kind of weird. It's kind of a strange little thing. You know, what would really make it, and so I'm saying there's 3 potential answers. You've heard me say that 6 times now already. You know, if this problem had an initial condition with it, watch this. If this problem had this initial condition, y of 0 equals 4. Or y of 0 equals 1/4. If it had this initial condition, then which interval would you pick? Do you know now which interval you would pick? Now you need to pick the right damn interval.
-2 to 2.
Yeah, thank you. You would pick the interval that contained the x value that is contained in the initial value. Right. The x value here is a 0, and that is in this interval. And so now we better pick the interval -2 to 2 to define our answer. Right. You're right. Subtle, kind of weird little, I don't know, subtle little details of these things. I mean, I like the big picture stuff. I like solving the DEs, but there are these little details we got to pay attention to in mathematics. All right, so I'm done with that question. We verified it's a solution, and we did this thing where we talked about the domain. We also, but different than the domain is this idea of picking an interval of definition, an interval on which we're working for the solution to the DE. All right. There's some interesting problems. I assigned some kind of, you know, I just picked and chose a few problems throughout here. I didn't assign 1 through 60. I picked a small amount of problems. Let's go, I'm flipping over to 1.2. I did one of these yesterday where we had to, they gave me some initial conditions and we had to find C. Let's try another one of these. Let me try. I'm going to try 14. So I just flipped over to 1.2. I'm trying to do some of this homework. Here's 14, just to show you how easy this homework is. Number 14 says, and it's got, again, it's got long direction sort of, they give me this y equals c1 e to the x, c2 e to the negative x. They call this y equals c1 e to the x plus c2 e to the negative x. They call this a solution to a DE. They actually call it a two-parameter family of solutions because it's got these couple of c's in here, c1 and c2. So it's a two-parameter family of solutions to the second order DE, y double prime minus y equals 0. So it's a solution to the DE, y double prime minus y equals 0. Okay? Right? And then they say this. Find a solution of the second order IVP. Hey, there's something for you. I didn't mention this word yesterday, although I did. An IVP is, the book talks like this, it's an initial value problem. That's what it stands for. When I give you a DE, when I give you a differential equation, it's not necessarily an IVP unless I give you initial values with it. When I give you a differential equation to solve, that's a problem. This is a problem to solve. If I give you initial values with it, then it's an initial value problem. It's an IVP. And what does that mean? That means instead of stopping at a general solution with C's, if we have initial values, we can find those C's and have a particular solution. So the solution to an IVP is a particular solution. You know, you find the C's. Now what I already have here is I have the DE, I have the answer. Well, what I have is the general solution. And if they give me some initial values, which they're about to give me, I can find C1 and C2. I think that's all this problem amounts to. But I'm trying to help you read the problem because that is a struggle for students here at first. I'm trying to do 14 where they say, find a solution of the IVP consisting of the differential equation and these given initial conditions. And for 14, it's y of 0 equals 0, y prime of 0 equals 0. The initial conditions are y of 0 equals 0, y prime of 0 equals 0. All right. So there's a lot there, but what am I supposed to do? Ultimately, this problem is about. I mean, ultimately, they could have shortened up their directions if they would have just said, please find C1 and C2. You guys understand that? That's really what this boils down to. Okay, and we practiced this once yesterday, but let's try it again. These things should help me find C1 and C2. I mean, this first thing says if you plug 0 in the function, you get 0. I'm going to try that. I'm going to get 0 for y if I plug 0 in. If I plug 0 in, e to the 0 is 1, e to the 0 is 1, and I'm getting this statement. So when I just used this initial condition and I ended up with that thought. You know, that's not enough to find C1 or C2. That's why we need another initial condition. And so we have one. But this initial condition is about the derivative. So I really need the derivative of the function. Well, that's no big deal. I'll do the derivative. In general, you do the derivative. Oh, by the way, this is interesting. I'm going to do this derivative. It's a constant times e to the x. What is a constant times e to the x? What the derivative is? Yeah, that's easy. That's just himself. The next one is a constant times e to the negative x. So what's going to happen?
Slap the negative 1 out front.
He's right. When I take that derivative of that e to the negative x, the chain rule is going to spit out a negative 1. So I'll get a negative sign out front. Hey. Okay, now listen. You saw me doing some funny things with the c's. You saw we can let c absorb constants in certain situations. I wouldn't do that here. I mean, we've already established C1 and C2, and now we take this derivative and we get a negative C2. If I let that absorb that, then I'm altering the value of C2. I mean, I shouldn't do that when I've already got sort of an established value of C2. Are you guys with me?
Are you saying that because it's C subscript 2 and not just C?
No, I'm saying it because I'm in the context of this, of trying to find C1 and C2. I don't want to start letting them change their values. I don't want to start letting C1 and C2 absorb constants and alter their look or their value. I mean, I did that in a different setting. In a different setting, I'm allowed to do that. But if I'm trying to solve for C1 and C2, I want them as they are, and I don't want to start letting them absorb constants. If I absorb this constant, it's not the same C2 it was, and I'm trying to solve for C1 and C2. So,
you like C3?
Yeah. So anyway, be careful about when you do that fancy C stuff. Anyway, not here. Here's the derivative. If I apply the initial condition, you plug in a 0 for x, you plug in a 0 for y, and you get this statement. Right, you guys? Is that right? That's right. E to the 0, yeah. Hey, this is kind of interesting. I wonder if I can solve this system of equations. This is might not be too cool. One thing I would do, I would just kind of add these equations. I mean, you can also solve and substitute. I would add them when you, guys, I see if you add them, these guys eliminate. But that gives me 2c1 equals 0. So what's c1? 0. And that's true. I mean, c1 is 0. That's what it says. Hey, if you plug that 0 back in there, what's C2? What's C2? 0. C2 is 0. Well, then I was trying to find the particular solution. This is the general solution. I was trying to find the particular solution that satisfies these initial conditions. Guess what it is? Y equals 0. It's this guy with a C1 of 0 and a C2 of 0. It's a boring, trivial solution. But technically, it's a solution. And it's the only solution that satisfies these conditions. That was a weird problem. I mean, it wasn't weird. It was just weird things happen sometimes. Usually when we get two numbers, we get a 1/3 and a -4/5 or some good old numbers like that. We got a couple zeros. This solution sort of went away to nothing. I could do this same problem with different initial conditions. You know, put in some different numbers here, and you could get some different answers. With these zeros, that's how this one came out. Hey, I want to make a comment. I'm not really going to redo this problem, but I want to just say something. So, you know, that is a family of solutions. The book refers to it as a 2-parameter family of solutions. I said that if you have a family of solutions, I don't really know what this one looks like, but anyway, for different values of C1 and C2, you might get all kinds of crazy. Here's a whole family of solutions, if you don't mind. Anyway, you know what I'm looking for? I'm looking for the one member of the family that satisfies these conditions, right? Right? And we've said that. I want to just say that in another way. Watch this. I want to find the one member of the family that goes through the point 0, 0. By the way, that's what that says. It goes through the point 0, 0. And when it goes through the point 0, 0, it has a slope of 0. By the way, that's what that says. At 0, its slope is 0. Right, you guys? That's kind of cool, right? I mean, it's just damn initial conditions. But those initial conditions are, what are they? They're a point and a slope. So another way to say this, you could say it in words. You could say, it has to go through the point 0, 0, and at that point, it must have a slope of 0. And that would be a sentence that's these initial conditions, right? Anyway, apparently the only answer to that is if you're going to go through 0, 0, and by the way, these curves are not right probably, but if you're going to go through 0, 0 and have a slope of 0 at that point, you won't be any of these curves apparently. You must be, I mean, the only guy that does that is this y equals 0, I guess. Or it's kind of a, he's the one member of the family. He's like a little boring member of the family, though, you know what I mean? All the other members of the family are interesting. He's like just the poor, boring kid. I don't know.
Well, wouldn't it be at just that instant? So it could still curve? And then
Well, it could, except we did the problem and found that it didn't curve. We found that the one member of the family that does satisfy these conditions turned out to be him. No, but you're right. It could have been anybody that went through that point and had that slope at that point. Right, here's a picture of somebody that could do that. Like, there's a good, yeah, that's going through that point and having a slope of 0 at that point. So it didn't have to be this boring y equals 0, but with this family and those conditions, it turned out it did have to be this. Right, right. Okay. I'm trying to do a little homework in 1.2. There's another little batch coming up that just that way I was just talking is kind of like 35 through 38, 39. They kind of talk like that. That's a good way to think. There's some pictures there. I'm not going to do those. There's a good problem, 45 and 46. You know, the truth is, it's really not good for me to do the homework before you do it. Because you get the fun of thinking about it and the fun of working your way through it without me. So I'm going to quit doing all that homework for you or with you. But I am calling your attention to some good problems, 45, 46, 51 is not too bad. We skipped section 1.3. 1.3 is telling me all about word problems, but I'm not going to do word problems until I get to chapter 3, so we'll just skip it. We're not doing that. Hey, what about up in 2.2? Did anybody try any separable DEs? Let's jump up to that homework. Anybody try any separable DEs that you want help with?
Yeah, I need help with 17 and 21.
Okay. Yeah, 17's a classic. Let's talk about him. And 21, I don't know. Yeah, let's do this. Let's do it. So up in 2.2, 17 is kind of a classic. Let's work on that problem. It is a DE. It is dp dt equals p minus p squared. dp dt equals p minus p squared. So this is a differential equation. Let me just ask you a couple questions. Is it first order or second order or third order? Or...
Second order.
No.
Not first.
It's first order because it's got a first derivative.
Nonlinear.
So that's not a second derivative.
Oh, okay.
Yeah. So that's a first derivative, and so it's first order.
So would I add parentheses then?
Yeah. So that's just p squared. Now, so it is first order. Okay. Is it linear?
Negative.
No, not linear. Why not? Because it has that p squared. Right, exactly. Right, that p squared makes it nonlinear, really. Okay. All right. So anyway, no big deal. It's nonlinear. These separable equations, when we separate and integrate, they can be linear or nonlinear. It kind of doesn't matter. The key is, are they separable or not? Not everything's separable. But I think this one is. I think we can, you just think of this as a big quantity and divide it, and you can get this separated. Do you agree?
Yeah.
I mean, if you think of it as a big quantity and just divide it, now it's separated.
Yes.
And so now that it's separated, you can integrate both sides. Let's integrate the right-hand side. Anybody know how to integrate the right-hand side?
Get rid of the d.
Well, you're integrating a 1 with respect to t. The answer is?
T.
T plus c, if you don't mind. Yep, cool. And now, to integrate the left-hand side, there's There's kind of only one way to do it. And you learned this in Cal 2, and you learned it somewhere in the middle of Cal 2, and I'll help you recall how to do it. I'm going to go over here to my scratch paper. I'm trying to integrate this. I need to factor out the p and look at it as a couple of factors, and then I can do this thing called, do you remember what to do?
I don't know, but it's going to be like 1 over p plus, right?
Yeah, well, right. I do that. There's this method called partial fraction decomposition.
Okay.
In your calculus book, it's section 8.5 of your calculus book, but it's partial fraction decomposition. I need to decompose this into 2 separate fractions. The method is, you set it up as, since it factors into 2 linear factors, you set it up as some unknown coefficient a over the variable p plus some unknown coefficient b over 1 minus p. This is setting up the I'm decomposing this fraction into 2 separate fractions. It's kind of weird. You know, all your life you've had these fractions and somebody says, well, get a common denominator and put it together. Okay. But for this integration technique, we need to not have a common denominator. We don't want it together. We want 2 separate fractions. So we're doing the opposite of getting a common denominator. We're decomposing the fraction kind of into its original denominators, maybe. I mean, what we're claiming is that this can be decomposed into these 2 fractions, and we don't know the a and the b. But with a little bit of algebra here now, we can find that a and b. The game was multiply by this common denominator right now. If you multiply by this common denominator, it cancels right here. You're left with 1. If you multiply it here, which you're supposed to do, and multiply it here, which you're supposed to do, then this p cancels. You get a times 1 minus p. You get b times p. How you guys doing? You set up the decomposition. You multiply by the common denominator. Do you remember doing this in Cal 2? Yeah. Okay.
It was chapter 8.
Yeah. Yeah. I mean, depending on how recent your Cal 2 was. Yeah. But yeah. Okay. Now you play this cool game. Watch this. This is easy. You let p be something very convenient.
Something that cancels out.
Something that'll zero something out. You're right. Like I'm going to let p be a 1. If I let p be a 1 and plug it in here, this term goes away. I get 1b equals 1. So guess what b is? 1. We just found out b is 1. Is there something else you could let p equal that's nice and convenient? 0. Let p equal 0. That will zero out that term. You plug in a 0 there, and you get a 1a on that side equals what's over here, which is a 1. So guess what? A is 1. It's not always that easy. Sometimes you get 2/5 and 3/7 and funny answers. But we decompose this fraction. So rather than integrating this, which I couldn't do, I couldn't integrate this in this form, I can integrate it now in its new decomposed form. In its new decomposed form, it is a 1 over p and a 1 over 1 minus p.
It kind of seems familiar. I would have thought about it.
Yeah. Anyway, but now that I've explained it to you, it's making sense?
Yeah,
sure. Anyway, now, so this partial fraction, it was a Cal 2 integration technique. I mean, we didn't learn it in Cal 1. It's fairly sophisticated, but as you can tell, it wasn't too horrible. But it was kind of, it's like a lot of busy work you got to do before you integrate. But now, once you've got to decompose, these usually are very easy integrals, like this one, ln of p, plus, and maybe I should put absolute value on that. And then this guy, that is another ln. Technically,
or 1 minus p, ln 1 minus p.
Yes, but there's another little technicality. To do this, to call this ln, you had to do a little u substitution. You had to let u equal 1 minus p. And if you let u equal 1 minus p, what's du?
It's a
negative dp. So yes, this is a natural log, but the u substitution process spit out a negative sign.
Gotcha.
And it equals this. Wow. We did it though. Hey, I'm going to stop here. If I stop here, I don't know if I really, I think, anyway, if I stop here, what's this? I would call this, what would I call this?
Implicit.
An implicit general solution. You know, if they want explicit, then what do I got to do if they want an explicit solution?
Solve for C.
No. Solve for, if I want an explicit solution, I want to solve for
The P.
the P, right, the function P. I want P by itself. I want P written as a function of T, right, that's explicit. Like I want Y written as a function
I
of
can
X.
see would that be a specific solution.
What'd you just say?
Like if we were to solve for C, like I said, then
Yeah.
what that would change is it wouldn't be general, it would be specific.
No, that ain't true. No, hang on. So, all right, so it's implicit because it's not solved for P. If we solve for P, it would be explicit, but it would still be a general solution because it has the C in it. So as long as that C is in there, it's a general solution.
Well, yeah, that's what I mean. Like if I solve for C and then I plugged in C.
Well, hold on. If there's a C hanging around your problem, it's a general solution. And the only way to get rid of C is, how do you get rid of C? Somebody has to give me
A specific form.
an initial condition. Thank you, an initial value. And if they would have given me an initial value, you know, then you plug that in, you find C, and then it would be a specific solution.
Gotcha.
So without this, we're stuck with the category of general solution.
Okay.
And now I'm just arguing whether we want it implicit or explicit. And I'm really trying to say that if we tried to make it explicit, it's kind of a pain in the butt. Solving for P here is another 6 steps. Do you want to do it? We should do it. Maybe we should. I mean, the way to solve for P here is kind of wild. You got to use your log properties. This is one log subtracting another log. So you could join those logs together and you'd have a numerator over a denominator. Is that okay with you?
Yep.
That's what the subtraction of 2 logs actually is. Now what, you guys? E both sides, yeah. If you E this log, it cancels. And then I think I'll just drop the absolute value. But that means I'm E-ing the other side, and of course that would be E to the T plus C. Do you remember how we would handle that?
E to the T times E to the C.
Yes, yes, yes.
Turn that E to the C to just a C in the front.
Yes. Yep, those are the steps, yep. Anyway, that helped a lot, but I still got to solve for P. I got my work cut out for me still. Let me think. I think I'd multiply this to this side. Yeah, I think I would distribute it through. I mean, what a pain. I would distribute it through P, C, E to the T.
Factor out C.
Well, move the, I just had it factored out. Let's move the P guy over here with the P guy. So P plus P, C, E to the T. And if I'm trying to solve for P, what would you do?
Factor out the P.
Factor out the P. Yeah. Factor out the P. Wow. And finally divide by that.
Yep.
That's a lot of algebra there at the end. But we did it, I think. I mean, you know, your book does some funny things. They might, I don't know how far you worked in 2.2, but they don't always go give you an explicit answer. Sometimes they leave it implicit, and they're not real clear on what they want you to do. They don't. I'll be clear. I'll say I want an explicit answer, or I'll say this one's a good implicit answer. I mean, I'll be clear in my directions, and you should know what those words explicit and implicit mean, so you can know where to leave your answer. But this might have been a good one to leave implicit. Whatever. I I did all that right. You guys were following my algebra there? Distributed, move that over, factored out the p, got divided. Yeah, I guess I'm good. Yep. Any other ones? He said, I think he mentioned another one. 21. Let's see what 21 is. In 2.2, dy dx equals x square root of 1 minus y squared. Dy dx equals x square root of 1 minus y squared. No initial conditions or anything. Okay. All right, separate and integrate. Yeah, I think I can do this. I can sort of see this. I'll multiply the dx up there. I'll divide by that big square root. So I'll have this. You guys okay with that? A couple little algebraic moves there. Now it's separated. Once it's separated, you can integrate both sides. And let's just go over here to the right-hand side. It's easy. When you integrate x dx, you get x squared over 2 plus c. And then this one is just, you either kind of know it or you don't know it, or you try to look it up. This particular book does have a nice table of integrals all in the front. You can kind of look stuff up, but it's arc sine. It's just the classic formula for arc sine. Which, and let's see.
So then if I move that up, that would only work.
It's not a good u substitution problem, right? It's not like a u to the 1/2 or a u to the -1/2, because there's no good du, right? If you called this u, du would be 2y dy, and there is no y dy. See, that would be subtle. Look, watch this. If there was a y on top, this is a great u substitution problem. Then it's
the y.
Then you let u equal what's inside the radical. You do the du, but without the y on top, it's not that. So what the hell is it? And it turns out to be arc sine, and it's not even a complicated arc sine. It's just the arc sine of y, I guess. So I'm done.
That's because you use over a, correct?
Yeah. Let's see. Arc sine is the
1 over a arc sine.
The variable squared over a squared. I guess my a is a 1. So it's the y over 1, technically. Right.
Arc sine doesn't have the 1 over a out front of it.
And it does not have the 1 over a in front of it. Although in this case, you wouldn't know because it's just a 1. But yes, you're right. It does not have the 1 over a. Hey, we're done. I would call this an implicit solution. If you wanted to make it explicit, what do?
Sine both sides?
Sine both sides. Take the sine of both sides. Yes. Because the sine will kill the arc sine, and you'll get y equals the sine of that whole side, not each term. You got to know your algebra. You're not doing each term. You're doing the whole side. Anyway, that's kind of a nasty looking explicit, but it's explicit. That's my explicit answer. Well, that's good, you guys. Listen, I think it's time for a little break. So I want a 5 or 6 minute break. I want to come back. I might push into some newer stuff. I'm glad I was able to help you with some homework to get you going there. But I'm going to hit pause and come back and do a